Okay, so first of all, what is deformation? Any idea? Deform. What does a substance become when it gets deformed? What does its shape become?
Wait, sir, I'll be right back in 5 seconds.
Yes, correct. Okay, so deformation means change in shape. Change in shape. And this is actually a property which is done due to a force. Okay, this force that causes deformation, what is it called? It's called deforming force. Deforming force.
Right.
Okay, now after this, tell me what Hooke's law is. This is easy. You've done this since O levels. Hooke's law.
When force is proportional to extension,
Given that,
it does not exceed the limit of proportionality.
yes. So you always need to give the complete definition. Now you gave me
Okay.
the complete definition. Force is proportional to extension, provided that the limit of proportionality is not exceeded. Limit of proportionality. Okay, what is limit of proportionality, by the way?
When force is proportional to extension up to a point.
Okay, so it is actually a point. The limit, it is a limit, right? It is a point. Okay, the point till which the force remains proportional to the extension. Beyond it, the force does not remain
It,
proportional to the extension. Meaning beyond this point, the Hooke's law does not apply. Okay, and what's the difference between limit of proportionality and elastic limit?
um, elastic limit is the highest point of stress the object can bear before deforming.
Before permanently deforming.
Yep.
Okay, because elastic deformation does occur, but permanent deformation, which is known as plastic deformation, occurs after the
Yep.
object exceeds the limit of it exceeds the elastic limit. So basically, you're going to define it in the following way. This is the point, the max point till which the spring regains its original dimensions once the deforming once the deforming force is removed. Okay, this is the complete definition of elastic limit. And by the way, elastic limit and limit of proportionality both are asked to define, and Hooke's law is also asked to define. And these are very easy marks. If you know the definition, you just need to write them down and you'll get the marks, full marks without any deductions. If you write down all the key points which I've given over here, okay? For Hooke's law, these are the two key points. For limit of proportionality, this is the key point, that force remains proportional till this point, and after it, it does not, it is no longer proportional. And then elastic limit, the maximum point. Okay, maximum point is also a keyword. Okay, till which the spring regains its original dimensions once the deforming force is removed. Clear? I
Yep.
would just take a photo of this. We can move on then.
Yep. Done.
Done?
Yep.
Are you copying or are you taking screenshots?
I took a screenshot and copying.
Okay, 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 all right. Then after the elastic limit and deforming force and limit of proportionality and Hooke's law, okay, so what do you think the graph of force against extension would look like?
What?
What do you think the graph of force against extension would look like?
Okay. A straight line passing through the origin.
Okay, a straight line passing through the origin, and will it always remain a straight line?
Not until the limit of proportionality.
Okay, not until the limit of proportionality is exceeded. Okay, so
Yeah.
this point till which it stays constant, can I call it the limit of proportionality?
Yes.
I can. Okay, and after this, it starts curving. Okay, will it start curving parallel to the x-axis, meaning parallel to the extension axis, or parallel to the force axis? It's extension. Okay.
Uh, it, Parallel to the extension.
And this is force parallel to the extension. Are you sure?
Yeah, because it curves
Yeah, but it will
downwards.
it curves downwards. Okay. So, but what if I had switched the axes? What if this was extension against force? Then what would you do?
It will go upwards.
Yeah, it will always become parallel to the extension axis. Okay. This is the key
Right.
point. Do not forget this. Okay. After this, where should I place the elastic limit point? Okay. This is the limit of proportionality. Where will the elastic limit come? Before the limit of proportionality or after the limit
No,
of?
after.
Okay, so shortly after the limit of proportionality, we'll have the elastic limit. Okay, now before the elastic limit, till the elastic limit, if I remove this force at the elastic limit, what will happen?
Um, it will regain its original shape.
Okay, and so what will the graph look like?
It will go. It will go parallel to that line, but downwards back to the origin.
You mean something like this?
Yes,
No,
but through the or to the no, no, not to the origin. Somewhere after the origin,
no,
on the x-axis,
no.
straight downwards,
Straight downwards, straight and
and
then downwards. What do
no,
you mean?
no, no, not that way.
You mean this
It
something
will
like
curve. No, that point will curve the same way. It's like equal to that, but reversed.
it's actually it follows the same path. This is the loading graph, and the unloading graph will have the same shape, exactly the same shape. Okay, because extension will return back to zero. Okay, this is the graph that you'll get within the elastic limit. Do you get it?
Okay.
Because
What about the other line that which is like shown on the graph
what do you mean?
below it?
Well, that is a line when it exceeds the elastic limit.
No, 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 no. That
This
like
one.
right under it. Okay, yeah, this one, this one.
Okay. So basically, you just told me yourself that it will regain its original shape, right? Regaining original shape means extension would become what? Would become zero again, right? Because
Yes.
originally
But
it
there
had
won't be another line.
no, before within the elastic limit, it won't be another line. It would be
Okay.
the same line. It would be the same path, okay? But if the elastic limit is exceeded, then the graph shape would change. And let me draw it over here. So basically, if the elastic limit is exceeded, this is the force, this is extension axis, and this is the curve. And let's assume this was our limit of proportionality, this was our elastic limit, and now we've exceeded it. So as soon as you remove this force from the spring, that spring would have undergone some permanent extension. And so as soon as this force is removed, this spring will try to, meaning removing the force means bringing it back to zero. So now the force will start coming back to zero, but the extension would return to a larger value other than zero. Okay, and basically this line, they are parallel to one another. If you look at them, these are parallel except for the curve. And this is the elastic limit, and this is the limit of proportionality. Okay, so this is how the curve goes. This is the loading curve.
Can they ask us to place where could elastic limit be?
Well, I don't remember something like that being asked, but maybe yeah, they, they can. But what happened? Why you sigh? Nothing, nothing. Sorry. I mean, like, it's not difficult. If even if they ask you to place where elastic limit is, you can, right? Just place it somewhere in front of the limit of proportionality. Get it? I can't hear you. Hello.
Oh, did you say something? Yes.
Um. Okay. I guess I'm sorry. It got wasted. You were not listening.
No, 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 I was listening. But you
Okay.
said something. I didn't get it.
Okay, no worries. I'm saying that elastic limit isn't that difficult.
Yeah, I heard that part.
Yeah, okay. That's what I was saying. Okay, this is the graph of unloading. Okay, now coming back to this graph. What does the area under this graph represent? What does this area represent?
Young's modulus.
No. What is Young's modulus, by the way?
Extrovert strain.
Stress over strain, and there's nothing to do. I haven't drawn a stress against strain graph anyway.
Area.
And by the way, Young's modulus is not the area anyway.
No, here, like that.
No, this isn't the Young's modulus.
No, I'm saying area because A.
This area is not the Young's modulus. I'm repeating.
I'm not talking about Young's modulus right now.
Okay. What are you talking about then?
We're asking to. Remember?
Okay, so let's try. Whenever you want to know what the area represents, always try calculating it. Okay, so how am I going to calculate the area of this triangle?
Half into length into breadth. That's going to be
Half into height into base,
half.
right? This is force, this is extension. So half into force into extension. Does this look familiar?
The
Force,
triangles. Oh, FX, right? Yep.
force into extension. What is force into extension? What's the unit of force? Newton?
N
What's the unit of extension? Meter?
M.
Newton meter. Are these the unit of work? Units of work? Force into distance. Is that work? Hello?
Yes.
Do you remember the formula for work?
Uh. Yes.
What is work? Is it a form of energy or force?
Force.
It is energy. Half fx represents the energy.
Force and energy.
The area under the graph represents energy.
Okay, right.
Okay, you don't know what work is?
Work done, right? Yep.
Yeah, work done. What is work done?
It's energy over time.
No, work done is energy.
Oh, sorry, that was, yeah, it's just energy.
Yeah, energy upon time, that's power, okay?
Right.
And the unit for work is actually Newton meter. Newton multiplied by meter, because the formula for work is force multiplied by displacement, right?
Okay, right.
And over here, we are also multiplying a force by a displacement. So force into displacement would give you the same units as work. Therefore, this area, since it has the same units as work, represents energy. Okay, because work is the energy. So this is actually the work which is done on the spring in extending it. So basically, let me give you a diagram over here. This is your spring. And let's assume that after attaching a weight to it, we did some work on it. Okay, this weight had a force downwards. And apart from that, the distance that this force made the spring move downwards is x. When you multiply force by x and multiply it by half, you get the work which is done on the spring. Work done on the spring. And by the way, this work done on the spring is actually a form of energy, which is known as elastic potential energy. Clear? Do you get it?
Yep.
So what does the area represent? Which form of energy?
Elastic potential.
Energy. Okay. So this is basically the type of energy which is stored inside of elastic objects. Okay, any object that can change its shape and regain it can store elastic potential energy. Even if you take the example of a rubber ball, a rubber
Or trampoline.
this will also regain its original shape after you do work on it in changing its shape, right? Why is
Right.
it able to regain its original shape? That's because some energy is stored in it. It uses that energy to regain its shape, okay? That's why these
Okay.
objects are able to regain their original shape. So
So
this
wait,
was,
what exactly was the explanation? I'll write that down. They might ask.
okay, wait. So basically the stuff that you need to write is this statement that area represents elastic potential energy. That's it. You don't need to write down all the other examples. That was just for your explanation,
Okay.
meaning for your understanding. The examiner won't ask you that.
Oh, okay.
Yep. And after this, okay. So since this is done, we can move on. Okay, so this was the area under the graph and which represented energy, and this energy is, okay. So now if I were to ask you to calculate the elastic potential energy stored inside the spring, how are you going to calculate it? Elastic potential energy. How are you going to calculate it? What formula did I just tell you?
F into F in works.
Yep, half fx. Okay, cool. We're getting it. So, and by the way, just keep in mind this x has to be in meters. This f has to be in newtons. So when you do that, if x is given to you in centimeters, you have to convert it to meters, okay? Do you know the conversion?
Yep.
Okay.
Centimeters to meters divided by 100.
Multiply by 100,
Yeah.
okay?
No, wait, that
And
would be meters to centimeters.
meters to centimeters is divided by 100. When you're going from, oh, wait. Meters,
Wait, sir,
oh,
that's a
oh,
bigger number than
yeah,
centimeters.
yeah.
No.
Sorry. Centimeters to meters is divided by 100. Yeah, correct. Meaning 10 raised to the power of minus 2, you just multiply it with this number. And when you're coming
Yep.
back, you do the other way around. Okay, sorry about that.
EP's unit would be NM.
Unit would be nm, or it's gonna be joules,
Okay. Yes.
the unit of energy, nm. Oh, it seems like a name of someone, some girl, nm.
Yep.
Okay, now let's move on. Uh, okay, so this was the elastic potential energy, and now we can even change this formula. We can modify it. You know that Hooke's law says F is equal to Kx. What's the modified form of this formula? Do you know the modified form? What's the other formula for calculating elastic potential energy?
Um,
Just take this F.
MGH is equals to half FX.
No. Basically, all you need to do is just replace this F by a Kx. And you'll get
Oh, okay.
half multiplied by Kx multiplied by X. This will give you half K x squared. That's the second formula for calculating elastic potential energy stored inside a spring using the spring constant, okay? Given that the spring constant is provided and this x is extension. Clear?
Yep.
Okay, so this was about the elastic potential energy stored inside the spring. Both the formulas are important and they are asked, okay? You are asked to calculate the elastic potential energy stored inside a spring. Now, if you look at this graph, before the unloading, before the permanent extension, this entire area actually represents the work which is done on the spring, right? In moving it to till here and extending it to this point. The work which is done on the spring is represented by this entire area.
Okay.
Now, as soon as the force is removed, The spring returns back to some permanently extended point. Let's assume it's here. In doing so, now we've got the area sectioned into two parts, the green part and the yellow part. So now basically, this yellow part is actually important to us. Examiner will ask you, what does this part represent? What does the area in between these two lines represent? So basically, this is the heat energy, the thermal energy or the heat energy that has been lost. This area between two lines, meaning the area between the loading graph and the unloading graph represents the heat generated or the energy which is lost. You get it?
Yep.
Okay. And this part, this energy represents, this area meaning represents the energy recovered. But the examiner, I've never seen a question being asked for the energy recovered, but I have seen the questions regarding heat energy. This is how you calculate the heat energy. If you are asked to calculate the heat energy, how are you going to do that? Well, for that, you'll need to calculate the entire area first, and from that, you'll need to subtract this triangle. Okay, and for that part, a grid paper will be given to you. Okay, a graph paper basically with the grid will be given to you. So first of all, you'll need to divide this into two parts. The entire graph needs to be divided into two parts. Let me draw it separately on different diagram. Okay, so basically it goes up to some certain point. This is force against extension graph. Okay. Goes up, gets curved, then it returns back downwards. This is unloading and that's loading. Now this is force against extension. You are asked to calculate the heat energy which is lost during unloading. Basically, this is the area which the examiner is asking you to calculate. For that, what you'll need to do is you first need to divide this entire graph into two parts. Basically, the linear part and the non-linear part. For the non-linear part, you're going to treat it as a trapezium. Okay. You're going to just treat it as a trapezium, and this is a triangle. You're going to calculate the area of this big triangle. You'll have the force, of course, you'll have this base as well, the height as well. You're going to calculate the area of this entire triangle, and then you're going to subtract from it this part. You'll get the heat energy of this region. This is the first part. Then secondly, what you're going to do is you're going to do over here, you're going to not do any calculation, but instead boxes will be given to you. Or you can do the calculation as well. What you can do is you can take the area of this.
Can you show an exam question on this?
Yes, I'll show it. Wait. Basically, what you need to do is you need to calculate the area of the entire trapezium. And then from that, you'll need to subtract this trapezium over here, this one. Okay, both of them are trapezia. So once you do that, you get this region over here. But now the questions which come in exam, they are usually on a grid paper. And there are many small boxes given to you on that. So you'll need to count the boxes in the region where you think this calculation is not possible. Okay, so let me see if I can find a question in the past paper booklet. Just a second. Yes, elastic potential energy is being asked over here. So a rubber band is stretched to by hanging weights on it, and the force extension graph is plotted. You just have a force extension graph. What is the best estimate? They're asking you the estimate of energy. What is the best estimate of the strain energy? Strain energy is actually the elastic potential energy. It's also called strain energy in the rubber band where it is extended to 30 centimeter mark.
So we'll check it from 30.
You'll need to calculate this entire area basically. You get it?
Okay.
Because area under the graph represents the elastic potential energy stored inside a spring, right? Over here they've given us a rubber band, but that doesn't matter. Okay. Calculation of elastic potential energy is the same. You just need to calculate the area under the graph. So now what you're going to do is you can't calculate the area of a curved object, right? So what you're going to do is you're going to approximate it. So approximation, let's take this part to be a triangle.
Or we
And
can take it to the trapezium.
uh, okay, you mean this entire region?
Yes.
No, actually that won't make this. We can take this part separately as a trapezium A2. This would be a bit more accurate. And then
Okay.
we can take this entire region as a trapezium as well, A3. Although you won't get the accurate answer, but you will get, definitely get an answer close enough to this, to any of these, and then you'll get a
Why
mark.
is this an MCQ? It seems to be long.
Yeah, there is always a single MCQ over there which is long on the exam. Okay, and the trick to that is you'll need to do it in the end. But actually, this wasn't that difficult because the answer options have a large gap in between them. So you'll definitely get an answer very quickly, even if you do the approximation very loosely. And if you take this entire part as a trapezium, and then you take this as a second trapezium, you'll get an answer still close enough to your correct answer. Get it? Now, apart from this, there is a second question. So basically, this was a question which says that the variation with the weight of compression of a spring is shown in figure 2.2. Okay, so basically this is compression against weight. Okay, so now compression is actually the reverse of extension, but it is still deformation. Why am I still calling it deformation? Because it is still changing shape, it is still changing length. So you're gonna treat it, the formulas of extension will be applied over here as well. But now what's the difference over here? Is this a force against extension graph or a extension against force graph? Is it force against extension or the other way around, extension against force?
The other way around.
Yeah, so what's going to be the area? It's going to be the area, the energy is going to be the area in between the y-axis and the graph, okay?
Okay.
Because area is always in between the graph and the extension or the compression axis. So if you are asked to calculate the area of this question, it's going to be pretty simpler. Actually, this is much simpler than the ones which they give with a curve in it. And in this part, you just need to do till any length which they ask. This is just a straight line. You just need to calculate the area of this graph. Okay, this is simpler. But what if this was a bit curved and, okay, not like this. Let's say somewhat like this. This was a curve and they asked you to calculate the area under this graph. Then you would have to approximate, okay? And for these questions, usually a range is given in the marking scheme for the correct answer, okay? You don't need to worry about your accuracy of the answer. It usually does lie in the range, but it should be close enough. It shouldn't be too vague. The approximations shouldn't be too vague. They should be good approximations, which should be as close as possible to the accurate answer. So basically somewhat like this. For this, again, you'll need to approximate. Okay, and the regions which you think you can't calculate directly, you just count the number of boxes which are coming in that part. And you can assume what each box area would be.
How do I do that?
Okay, now for instance, in this case, I'll tell you, in this case, for each box, what's the area of each box? Okay, so 1, 2, 3, 4, 5. 5 boxes still here. And 5 boxes still here. These 5 boxes, what's the area of these 5 boxes? Okay, wait. Counting the boxes, okay, it's more like this, 1 centimeter against 1 centimeter. So 1, 2, 3, 4, 5. If you're counting 5 boxes are representing 0.5 centimeters. If you look at this graph, 5 boxes represent 0.5 in this
Right.
graph, and on the x-axis, it's again 5 boxes, but this time it's 1, 2, 3, 4, 5. 5 boxes representing 1, 2, 3, 4, 5. 5 boxes representing 5 Newton on the x-axis. So it's gonna be okay. So what you need to do is just count the number of boxes, and for each box, assume that each box means one unit of an area. That's the major reason why they give you these boxes. These small boxes, do you see the small boxes over here? So if I want
Yep.
to, calculate the area, I want to calculate the area using the boxes method, for example, of this part, if I look at the number of boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, approximately 10 boxes are in here. 10 boxes mean the 10 units area, meaning it's the energy is 10 joules. But given that the y-axis is in, okay, it's in centimeters, so you'll need to convert that as well. It's not going to be 10 joules. It's going to be different than that. It's Newton centimeter, so you need to convert the centimeter as well by dividing it with 100. It's going to be 0.1 Newton meter, somewhat like this.
Okay.
Okay, wait, I think this is becoming a bit confusing. Okay, just remember one thing, you need to approximate. You just need to approximate if a curve is given, and you just need to
Right.
calculate the area, and that's it. You're gonna get the area as close as possible. And by the way, for such questions in which you just need to simply calculate the area, but there's a lot of working, the marks are usually 4. And these 4 marks are actually for all the working that you do to calculate the area. Let me
Okay.
see if I can find another question. Basically over here, what we need to do is, what if we need to calculate the area under this graph? The first thing is you just need to divide it into 2 parts. Get this area. This is a triangle. You can just calculate it by half. This length, which is given on the x-axis, you can measure it. It's somewhere around 1.8 centimeters. And on the y-axis, the force, and then you can calculate that. And apart from that, for the rest of the graph, you first make it convert into a regular figure. Okay, for example, over here, you just divide it into a trapezium. You find the area of this trapezium by the regular method. Half multiplied by this height multiplied by the sum of the 2 parallel sides, right? You know the formula, right? Hello?
Okay. Yep.
Okay, once you do that, for this remainder, you just count the number of boxes which are present inside this remaining region. The number of boxes that you get, you add the number of units to the area answer that you get. For instance, let's assume there are 20 boxes inside of this, just assuming, okay? 20 boxes are present inside. The area that you got from here was, let's assume it was somewhere around 120. The area you got from here was, let's say, it was 29. Okay, just assuming. It was, let's say, it was a bigger value, 50. So now what you're gonna do is, when you add these two up, you'll get the regular area. But for those small boxes, you add the number of units to this area as well. Meaning the number of boxes that you've counted, you just add it to this unit. So it's gonna be, this is 170, you add the 20 to it, it's gonna become 190. That's gonna be your approximate area. So basically the number of boxes, each box would represent 1 unit of area. Now do you get it what I meant by box counting?
Yep.
Okay. Even if you use the boxes to count the number of boxes under this graph entirely, you'll get the area very close to the actual area, very close to these values. Okay. But
Okay.
counting the boxes is very time consuming, and it will use up a lot of time. So it's better to go with the approximations. Should I move on?
Yep.
Okay. Now once this area under the graph is done, now what if I ask you, okay, tell me the 2 formulas of energy.
Half fx
Half of x and,
and half kx squared.
okay, and what form of energy is this?
Uh, Elastic potential energy.
Okay, and on the graph, how will I find the value?
It's the area under the graph.
Okay, and area under the graph in between what axis?
Limit of proportionality.
No, 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 no. I mean in between the graph and which axis?
The x and the graph.
Okay, you mean the extension axis, right?
Yes.
Okay. Now, in addition to this, there's one last property of the graph that is left, and that is the slope of the graph. What does the slope of the graph represent? Any idea?
Young's modulus.
I'm asking about the slope of the force against extension graph, not the stress against strain graph. Yeah, Young's modulus, well, that's true only for the stress strain graph, not for the force extension graph. What about the force extension graph? What do you think the area of the slope of this graph represents? Calculate the slope. How are you going to calculate the slope?
That would be like y2 minus y1 over x2 minus x1.
What's the y in this case?
F,
And what's the x?
extension.
Okay. Force against extension. What is this quantity equal to?
Newtons divided by meters.
Do you remember Hooke's law?
Oh, right.
Do you remember Hooke's law?
Yeah.
So if I rearrange this formula, what is it equal to? What is this?
Constant.
Which constant?
Hooks.
Hooke's constant. Okay. Do not forget these small details. These are important. Okay. The slope of this graph represents the Young's modulus. Sorry, not the Young's modulus. The Hooke's constant.
Okay.
Okay. So this was pretty much everything about the graph. Now, coming to the combination of springs. How to calculate the total spring constant of two springs which are in parallel to one another. Any idea?
Yes.
Okay, I'm saying that a single spring has a spring constant of K, and if I take two springs in parallel to one another, what's gonna be the total spring constant of these two springs? You know how to calculate this from that lecture of deformation. The force is F.
2K.
2K, are you sure?
It's going to be divided because there are two springs, so it's not going to be 2K.
It is 2K. But you don't know why. You are saying that it's going to be divided. Do you know what the spring constant actually represents? It represents what property of the spring? Hello? What is
Yep.
this property?
Stiffness.
Stiffness. What does stiffness mean? Does it mean the hardness of the spring?
Yep.
How easily the spring is extended is represented by the spring constant. So now, basically, if you have a spring with a spring constant K, and if you have another spring with a spring constant 2K, the spring constant 2K would be harder to extend as compared to K. Okay, this is what the spring constant actually represents. Now, if you know this, tell me, will these two springs, when they are attached in parallel, will they be harder to extend or will they be easier to extend as compared to this single spring?
Harder to extend.
Yes, they are going to be harder to extend. So harder to extend actually means the spring constant is going to become greater than this single spring constant. Is that so?
Yep.
Okay. So whenever you have two springs in parallel to one another, their spring constants are going to get added and you'll get the total spring constant 2K. And now basically the thing is, if you remember your resistors, remember resistors when they were attached in series, how did we calculate the total resistance of resistors in series? We just added their resistances, right, to R. This was the total resistance of resistors in series, correct?
Yep.
So for springs, to calculate the total spring constant in parallel, if we've taken the springs in parallel, we're gonna use the
Okay.
formula for the series resistors. Clear?
Yep.
And what about the springs which are attached in series? If I have one spring and then followed by another spring, and for a single and they are now attached by a force F. For a single spring, the spring constant is K. What's going to be the total spring constant of this combination? I'm waiting for your answer. Come on. Say anything. Come on.
2K, dude.
It would be 2K2.
2K.
2K. Why?
Oh wait, K square.
K squared. Are you serious?
I don't know.
Okay, so you need to try. Remember for springs in,
For parallel, I mean for
these are in series, right? Just now I told you for parallel springs, you're going to use the formula of series resistors. For series springs, you're going to use the formula of parallel resistors. Okay?
so 2K.
No, it's going to be K upon 2. Get it?
No.
Now, 1 up, okay, listen, 1 upon RT equals 1 upon R1 plus 1 upon R2. This is the formula for parallel resistors.
Yep.
So what's going to be the formula for series springs? For series springs, it's going to be 1 upon KT equals 1 upon K1 plus 1 upon K2 and so on. So in this case, since these are identical springs, we can just use product upon sum to calculate the total spring constant for two springs. So it's going to be the product is K squared upon 2K. The K and the K squared will get cancelled out. So K upon 2 is left. K upon 2 is the total spring constant of two springs which are attached in series. So now, since the spring constant is less, it is half the original spring constant. Can I say that these two springs, when are attached in series to one another, they become softer to extend, they become easier to extend, they become less stiff?
Okay.
Can I say that? Come on, yes, no.
Yes.
Compare the spring constants. Is the spring constant value less than the original spring constant?
Yes.
It is half, right? So that's why it's going to be softer.
Mm-hmm.
Yeah. Now, I just told you that the graph gradient represents the spring constant. So if I have three lines, K1, K2, and K3, which of these will have, which of these three springs will be the hardest to extend?
K3
K3, reason?
because it has the highest something. Wait.
Highest slope, come on,
Highest,
something.
yeah,
High
I
slope
forgot
means,
the term word.
okay, high slope means what quantity is high?
The constant.
Yep, high spring constant, correct. There's another way of looking at this as well. So basically, if you have two springs which are attached in parallel to one another to a force F, this is your force F, this force will get divided in between these two springs, and each spring will experience a force of F upon 2. And both of them will be extended by the same extension, E.
Okay.
If both of them are extended by the same extension, E, then to calculate the total spring constant, what we do is we actually, okay, this E actually is not the same as the E of single spring. Now, let me just clarify that 1 second. Let's assume there was just one spring experiencing the same amount of force and it had a spring constant K. In this case, if we apply Hooke's law, F is equal to Kx, the extension is going to be F upon K.
Okay.
Now, in this case, if I were to calculate the uh, spring constants, basically the forces have halved. Force experienced by each of these springs has reduced to half of its original value. That actually means that the extension has also become half, and both of them are experiencing the same extension. The extension equal to the extension which is given over here, it is half of that. If I were to calculate the total spring constant, it's going to be F, yes, F upon X. The force, the total force is still F, the total force. I'm not talking about the individual forces, I'm talking about the total force. Is it still F? The total force is actually the force which is hanging from here. Hello?
Yeah.
Are you listening?
Yep.
Okay, so basically I told you the total force is still F. And when you divide this total force by the total extension, this time the total extension is half of the original extension, because each of the springs individually is experiencing half of the original force, half of this original force.
All right.
If with this force extension was X, with the half force extension is going to be half. If you place X upon 2 over here, the 2 will go up, right? Now 2F upon X, what is F upon X? Is it the original spring constant, K? If you rearrange this formula, the spring constant is F upon X.
Yes.
So now for this combination, this has turned into twice the original spring constant.
Okay.
So I told you that for two parallel springs, to calculate the total spring constant, you just add their values to get 2K. That also has been proven from this method as well. I'm gonna take one more example over here, just a second. If I have, let's assume I have 3 springs over here. They're all attached to the same force F. Now, if I had a single spring, which was attached to the same force, and at that time the extension was X, and if the extension was X, and I use the formula F is equals to Kx, the value for K becomes F upon X. Now remember this. In this case, when we have three identical springs attached in parallel to one another, in this case, the force experienced by each individual spring becomes K upon 3. It gets divided in between the 3 springs. Get it?
Uh-huh.
If it gets divided in between the 3, oh sorry, not K, it's F upon 3. Okay, it's F upon 3. I just mistakenly wrote K, it's F upon 3. Now, if the force gets divided in between the 3 springs, what will the extension become? The total extension of each spring. You know that force is proportional to extension. If each spring is experiencing 1/3 of the original force, then their extension will become 1/3 of the original extension.
Right.
Okay, now if I were to calculate the total spring constant, how am I going to do that? It's the total force divided by the total extension, right?
Yes.
The total force is still F, but the total extension now has become 1/3 of X, the total extension of each individual spring. If it has become 1/3 of X, if I place the X upon 3 over here in the denominator, the 3 will go up. This becomes F upon X, right? 3F upon X. What is F upon X?
The constant.
Yeah, so it became 3K.
Uh-huh.
Now do you get it? Now is it a bit clear?
Yes.
Or you could just add them directly to get your total spring constant 3K. This was just a method to prove it that yeah, it is gonna be 3K. Clear?
Yep. Clear.
Okay. The same can be applied on the parallel springs as well. So now in parallel cases, this is the force F. In parallel, the same force is being applied on both the springs FF. And their extensions are, let's say this is, if this is, the force is F, the extension is gonna be EE, right? Extension is gonna be, meaning I didn't take the E as a variable over here, I took X as the variable. Okay, so if the force is F, extension is gonna be X. What's gonna be the total extension? The total extension is gonna be 2X. What's the total force? The total force is still F. If the total force is
Okay.
F, the total extension is 2X. What's the spring constant? Spring constant is the total force divided by the total extension. The total force is F. The total extension has become 2X. What is F upon X?
The constant.
Constant upon 2 is the value that we get.
Right.
Yes. Now is it becoming clear?
Yep.
Okay. Now let me trick you a bit. Okay, if I have 2 springs, okay, in fact I have 3 springs attached in parallel to one another, and then beneath them I have 2 more springs, and all of them attached to the same force. Now, what's going to be the total extension? Any idea? Sorry, what's going to be the total spring constant of this combination, given that each spring has a constant of K? You can use any of the 2 methods.
K over 5.
K over 5. Okay, K over 5. Now let's see. This is F, right? This F will get divided in between these two, become F upon 2 and F upon 2. And by the way, okay, let me use a shortcut first. Basically, using the shortcut is much faster than using this longer method. So in the shortcut, what you need to do is you just need to identify the springs which are in series and which are in parallel, and then just use the formulas. These 2 springs, are they in parallel or are they in series?
Parallel.
So what's going to be their spring
2K.
constant? Okay, it's 2K. And what about these 2?
3K.
It's 3K. Okay. What about these 2 combinations? Okay, now listen. The 3K and the 2K actually means that you can think of it this way. Instead of the 3 springs, you can assume them to be a single spring of a spring constant 3K. And for these 2,
2K. Okay.
2K. Now, what's going to be the total spring constant? Product upon sum?
5K.
3K multiplied by 2K divided by 3K plus 2K shall give you the total spring constant. Remember the parallel resistors formula?
Yes. Yes.
So 3 2s are 6K squared divided by 5K. KK, it's 6 upon 5K.
Okay.
Now do you get it?
Yep.
It's not K upon 5, it's 6 upon 5K. So basically, I think you did reach here, but you were not aware of this situation. You were not aware
Yep.
in series with one another. And so since they are in series, you could just apply that formula and you can get your answer. So this was a shorter method, and then you can also verify this by using the longer method as well. For the longer method, it's pretty simple. This is
No,
force,
this
right?
is
Yeah, this one is fine. Okay, this one is fine, but I'll still explain that method. This is force. Each of these springs will experience the half of the original force, and each of these three springs will experience 1/3 of the original force.
Over 3. Yep.
And so if this is F upon 3 and this is F upon 2, this is F upon 2, this means the total extension becomes E upon 2. And if this is F upon 3, the extension becomes E upon 3. What's
Your
the...
voice is breaking off a bit.
Hello?
Yes, now it's better.
Okay, so this is E upon 3, this is E upon 2. Oh, wait, the battery is about to die. Wait, just let me connect my charger. Okay, now, basically this is E upon 3 and this is E upon 2. And I just told you that these two are in, meaning this entire combination and this entire combination, they are in series with one another. The total extension is going to become E upon 3 plus E upon 2. And if you take the LCM, what's going to be the LCM? It's going to be 6, right? 3 times 2. And if you add them in, it's going to be 2E plus 3E. And this is going to become 5E upon 6. This is the total extension. The total force is still F. So what's going to be the total spring constant? F upon the total extension. The total extension is 5E, and then the 6 will go up. And then F upon E becomes 6 upon 5K. Get it?
Yes.
Okay, so now you get it. Okay, so this was the combination of springs. After this, we can move on to stress and strain, the last part of this chapter, stress against strain. What is stress by definition? What is stress?
The amount of force it can bear.
Can bear before breaking. That's ultimate tensile stress that you just defined. Ultimate tensile stress is actually the amount of stress that an object can bear before breaking. But what is stress itself? Hello, I'm asking something.
Oh, force over area.
Force over which area?
The wires.
Cross-sectional area, not the wires area.
Right.
Okay, this term cross-sectional, this is a key term. Without this, you won't get the mark, okay? So whenever you are supposed to define what stress is the force per unit cross-sectional area. Okay, what is strain? What is strain?
Extension into Thompson. I forgot the formula.
Extension into what?
I forgot the formula.
Okay, extension into, I forgot the formula. Basically, strain is a ratio. Now, do you remember it?
Half into K into extension.
No.
Okay.
Okay, so what is strain? It is a ratio.
Ratio extension to the original length.
Yes, to the original length. And original is the key term you must remember. Okay, we did stress definition, we did strain definition. There's another definition called the Young's modulus, which you've been repeating again and again. Young's modulus. So अब ये भी बता दो कि what is Young's modulus?
Stress over strain.
Yep, it's the ratio of stress to strain. Okay, so we've done stress, we've done strain, and we've done their ratio. Now let's go into their detail. So basically, if you have a wire and on the same wire, there is some force being applied. Sorry about that. There's some force being applied and it has constant cross-sectional area A. What's going to be the stress is going to be the force upon the original area. The original area can also be written as pi r squared, right? Or it can also be written as pi d squared upon 4. Both of them are the same thing, where d represents a diameter. Remember diameter of a circle and the radius of a circle.
Yep.
Okay. Now, apart from this, if you talk about the extension of a wire, okay, so if you talk about the extension of a wire, if you have the same wire and its original length was L, and now after applying some force on it, the length becomes, let's assume it becomes L prime. What's going to be the extension? It's going to be L prime minus L. And L prime minus L is the extension. The original length was L. If I ask you to calculate the strain, it's going to be the extension, which is L prime minus L, divided by original length, which is L. And to calculate the Young's modulus, you can just use these two formulas, stress over strain. Now let's go into a bit more detailed formula of the Young's modulus. So basically, I just told you that the formula for stress is force upon cross-sectional area, whereas the formula for strain is extension upon the original length. Clear?
Yep.
Now, so what's the formula for the Young's modulus? Young's modulus, by the way, is represented by capital E. Young's modulus is equal to stress upon strain if you plug in F upon A over here and E upon L over here, we'll get a new formula for Young's modulus. Okay, and now let's do that. What is that formula gonna be? Any idea?
Fx
Yeah,
origin length minus extension.
Fx over Le. Okay, let me just write it down. Basically, the Young's modulus is equal to stress divided by strain, right? The stress is this. If you reciprocate it, we can change it to a multiply sign, and this is gonna become FL over AE. So the Young's modulus formula is FL over AE. There is no negative sign in there. Okay, FL over AE, and this formula is actually the most important formula of the entire chapter. This has been asked so many times in the past papers. So this is actually the most frequently being asked formula of the past papers for the Young modulus. If you have the length of a wire, if you have its cross-sectional area and extension and force, you can calculate its Young's modulus. And by the way, this Young's modulus is material dependent. So as long as you don't change the material, the value of the Young's modulus will not change.
Okay.
Now, let me give you an example over here. If you have a wire of cross-sectional area A, and if you have another wire of a cross-sectional area 2A, given that the length is constant, force is constant, cross-sectional area is constant, even the Young's modulus is, also wait, the cross-sectional area is not constant. Young's modulus is constant, and I asked you to calculate the extension when the same force is applied. How are you going to do that? What's going to be the extension when the same force is being applied? Assuming that everything of these, every other thing in this formula is the same, except for the extension and the area. I gave you the area, I want you to calculate the extension, how to do that. What's going to be the extension of this second wire as compared to the first one, if the first one had an extension of E? given that both of them have the same length. Both of them have the same Young's modulus, meaning have the same material. What's going to be the extension of this one?
The extension is going to get divided by 2
Why?
because the area is doubled.
Mm-hmm.
So it's harder to
Explain.
increase the length with a greater cross-sectional area.
Yeah, this is correct. Actually, you're not going to explain it that way. You're going to explain it using this formula. You know that if you make the extension the subject, the formula becomes FL over A capital E, right?
Yep.
Given that FL over E is constant, what's the relationship between the area and extension? Are they inversely related?
Inversely proportional. So
If they are inversely proportional and I double the area, the extension will become half.
half.
Okay? This is how you're going to explain it.
Okay.
Now, so see, you know the stuff, you know the answers, but you don't know how to explain it. Okay? So this is how you're going to
Yeah.
do it. You better stick to the formulas for almost all of the explanations in physics.
Right.
Now,
Okay.
okay, now let me trick you. Let's say I have two wires and they're made up of the same material. And the first one now has a cross-sectional area of, let's say, 2A. It has a length of, let's say, 2L. It has a force of F. It has an area length force is given to you. What's going to be the extension of this wire if the second one has an area of A, length L, force F, and had an extension of E? I've just made
What
this
did you
question up.
ask?
I'm asking you what's the extension of this first wire?
Okay. That
Okay,
will be divided.
wait. Sorry. I'm not asking you the extension of this wire. Just a second. I'm asking you something else. Just 1 minute. Let's assume the extension given to you is E as well. Okay, not E. Not E. Definitely not E. Um, this extension is EX. This extension is E. Okay, not EX, EY. Just assume this is 3E. What's the, and let's say the first one has a Young modulus of E. What's the Young modulus of this one? Okay, now this is the question.
I'm so confused. What is happening?
Okay, wait. Basically, what's the formula for Young modulus?
FL over AE small e.
Okay, FL over A small e. Now, this was one wire that is given to you in which the extension was E, area was A, length was L, and force was F. Length F, L, A, everything is given to you. We have a second wire of the same material having an area of which is double the original area, length which is also double the original length, extension which is thrice the original extension, force of F. What's going to be the Young modulus of the second wire? And this is a trick question.
A is to I don't know.
What do you mean by I don't know? Don't you have the formula in front of you?
Yeah, but like why is it to L and to A? If the
Um,
L is doubled, won't it be half?
it can be 2L and 2A at the same time, and they both of them will get cancelled. Okay, let me modify this a bit. The extension is the same, okay? Now,
E is going to stay E.
E is going to stay E, and the reason for that is,
As you said, 2 and 2 cancels out.
that's why it's going to stay E.
It remains the same.
Okay. What about this thing? Any hint from here?
Same material.
Didn't I just tell you that Young modulus is material dependent?
Right.
So it's just like resistivity. Remember
Since it's the
resist?
same material, it won't change. It will stay the same.
Yes, definitely. You didn't even need any calculation. Okay? As long as the material stays the same, the Young modulus will stay the same, regardless of whatever dimensions of that material are. Get it?
Yep.
Finally. Okay, there is another way of writing the same formula. Extension is equals to FL over AE. Instead of writing it as A, I can write it as pi d squared upon 4, right?
Yep.
So if I plug this over here, it's going to become FL over pi d squared E, and then the 4 will go up. This is another formula of Young modulus, and now examiner can change the diameter as well of the wire and then tell you what's going to be the new extension or new length or the new force or anything like that. But if he asks you the new Young modulus, as long as the material is the same, the Young
It'll stay the
modulus
same.
will stay the same. Correct. And okay, now let's assume you had original okay, original wire of diameter D, length L, force F, and extension E as well, and Young modulus of E. You have a second wire of the same Young modulus. You need to calculate its extension if the diameter has doubled, keeping everything else the constant. Now, what am I gonna do? What's gonna be the new extension? Any idea?
Oh, what changed? Okay, diameter. Okay,
Yeah,
became doubled.
use the same formula, right? Now, make extension the subject. What's the relationship in between them?
Decreases.
Okay, tell me the exact
Halves.
value.
Halves.
Will it half?
Yes.
No, there's an inverse square relationship.
Oh,
So what will it become?
it'll stay the same.
No, it will decrease, but it will not be half.
Four
Basically,
times.
yes, 4 times. If you place a 2 over here instead of the d, and if you square it, it's gonna become 1 upon 4 times d of the extension, right? 1 upon 4 times the d squared. So since the d squared got multiplied by 4, the extension is going to become 1 upon 4 of the original extension.
Right.
If this would have, let's say, increased by 3 times, then what would have the extension become? Would have become 1 upon 9 times.
Okay.
Inverse relationship. What if inverse square relationship? What if this was 4 times increase? What would have been the new extension be? If the diameter had increased by 4 times,
It'll decrease by 4 times.
will it decrease by 4 times?
Oh, 16.
It will become 1 upon 16 of the original extension. Get it?
Yep.
All right. What if it's the diameter increased by 5 times? What will the new value of extension?
25. 1 over 25e.
Okay, clear. So this was about the Young's modulus. Now coming to the graph of stress against strain. This is the last graph of this chapter, and we are done with this chapter. Okay.
Then we're done with the class?
No, we still have
What?
we still have a lot of time.
After we're done with this, then can you compensate for the
Stress against strain graph. For this graph, basically, you've done the definition of Young's modulus, which is the ratio of stress to strain. What's going to be the Young modulus in this graph? It's going to be the slope of this graph.
the gradient?
Yep. And the gradient is going to be stress divided by strain. And if you calculate the area of this graph, it's not going to be the energy of the graph, but rather it's going to be something different. And that's a new quantity. Okay, wait, let's move on. Area under graph is going to be half multiplied by stress multiplied by strain. Instead of the stress, you could write force upon area. Instead of the strain, you can write extension upon length. And this is half, right? Which is equal to the area under the graph. Now over here, force into extension, this is actually energy, right? We know that.
Yep, work done.
Half force into extension is energy, and area into length. Actually, this entire thing is the elastic potential energy, right? Which we know half Fx is elastic potential energy from the spring. Hello, Parwa, can you hear me? Yeah, half Fx, this entire quantity, is the elastic potential energy.
Yep.
Spring. And area into length. What is area into length?
B?
Yeah, volume.
Oh.
Cross-sectional area into length is volume. So this is going to become elastic potential energy per unit volume. Per unit volume. Elastic potential energy per unit volume can be calculated using the area under this graph. Okay. Although the examiner won't ask you to calculate the area under the graph, what he can ask you is, what does the area under the graph represent? So it represents the elastic potential energy per unit volume of a stress strain graph. Clear?
Yep, clear.
Now, what's the relationship in between this graph and the force extension graph? Let's look at this relationship. So basically, in this graph, in both the graphs, there is a relationship in between their gradients, between their slopes, basically. So now the slope of this graph represents the K spring constant, and the slope of this graph represents the Young modulus. This Young modulus can also be written in terms of K. Young modulus is equals to FL over AE. And now you know that force upon extension. What is the force upon extension?
K.
KL upon A is equals to the Young modulus. Now if you make this, if you rearrange this and make K the subject, it's going to become EA upon L. So you can use the gradient of this graph to calculate the gradient of this graph. By multiplying EA and dividing it by L, you can get the spring constant K. What is the spring constant equal to? EA upon L.
Okay.
Yeah. So copy this or take a screenshot, or have you copied it?
I'm taking a screen.
Okay, so now if you make FW the subject in the first equation, it's going to become mg plus ma, right? अब क्या हुआ है, एक्चुअल वेट mg था, बट जिस एक्सेलरेशन से ये लेफ्ट ऊपर की तरफ जा रही है ना, एक्सेलरेशन a, उसको आप अगर m के साथ मल्टीप्लाई कर देंगे और इस एक्चुअल वेट में ऐड कर देंगे, तो दिस विल गिव यू अ वैल्यू which is larger than the actual weight, and this is going to be your apparent weight of the person going upwards. And it's going to be larger than the actual weight. So when you are going up in a lift, your weight actually appears to be greater than your actual value if you stand on a scale. And then if that same lift is coming downwards, then the formula becomes a bit different. It's going to be FW plus mg equals ma. Now if you make up the subject, it's going to become ma minus mg. meaning the acceleration with which it is falling, you take the difference to get the apparent weight. And if this if the string breaks, the lift falls, and the person becomes unconscious, then what happens? The acceleration, it actually becomes equal to the acceleration of free fall, and this MA actually becomes mg minus mg. And what does the apparent weight become? It becomes 0.
Okay.
And so the person becomes weightless. Okay, so if during that same scenario, keep yourself in that same scenario, and if you drop, let's say, a ball at the in that same scenario, that ball will remain in the air and it will not fall. It will appear to you as if it's in the air and it will not fall. And you are also standing here without any weight, and the lift is going down. Unless you reach a terminal velocity, then a time will come when you'll hit the ground with that same velocity. Hopefully you won't. Okay, just a bit of work done.
F into D.
Yep, F into D. And what's D?
3.7.
No, that's the problem. F multiplied by D is equal to work, and D is actually the distance traveled in the direction of force.
So we find the circumference.
Yes, we find the circumference, we multiplied by 1.4. 144. Yeah, the circumference is 2 pi multiplied by r, which is 3.7. And this turns out to be, if you have a calculator, please do it.
Okay.
It's going to be 23.25. Okay, 23.25 meters. This is the circumference of one circle. 23.25. Yeah, 23.25. Take it till two decimal places. Now, this is the circumference of one circle. How many times are we turning it? Turning it 144 times. Turning it 144 times actually means what's the total distance that this horse covered in this hour? It's 144 multiplied by this, which is 3,347.68 meters. We got the total distance that the horse traveled, and the force that it applied was 800 Newton. So what's going to be the work done? It's going to be force multiplied by the distance that it traveled. The force is 800, the distance is this much, 3347.68, and this should hopefully turn out to be 20K. No, it's a much larger value. Let me see. 3347.68 multiplied by 800. No, that's not the correct answer. Just a second. 23.25 multiplied by 800. Yep, that's the answer. Okay, wait. You don't need to do this part. Reason for that is because this distance, this 144, is actually the distance traveled in 1 hour. And if you read the question again, the examiner is asking you to show that through one revolution. Okay, they are asking us for only one revolution, not for all 144. The answer that I was calculating, it was for the entire 144 revolutions. For just one revolution, we know that the distance traveled, meaning for one circumference, is this much, 23.25. And when we multiply it with the force, which is 800, the answer to this turns out to be approximately 20,000. It should be 20,000. Please do the calculation. What's the answer?
23.25 into 800?
Yep.
18,600.
18598.
No,
1860851. Basically, for the pi, did you use 3.4? Did you use the value of pi?
No.
What did you use instead of pi? Did you use the symbol given in the calculator?
Wait, for what?
For the pi, this thing.
Oh, I had to. I just typed 23.25.
Wait, what did you use for 2 pi?
Wait, why would I use 2 pi?
Okay, you use 23.25. Basically, use this value.
Okay, I had to use that for an accurate value though.
Yeah, you have to use this value in your calculator. Reason for that is because this is going to give you a more accurate answer.
Right.
And this is the answer that we get. This is approximately 20,000 if you round it off to one decimal or one significant figure. Watts.
Okay.
Actually, no, not watts, it's joules. And after that, the second one is they're asking us to calculate the average power and in SI unit. So what do you think should I do? What's the formula for power?
Work done over time.
Okay, how to do this? What's the total work done and what's the total time given to us? The total time given to us is 1 hour.
Mm-hmm.
1 hour
60.
means 3,600 seconds.
Oh, I was taking 60.
Oh, nice, nice. You mean you were taking 60 minutes?
Oh, God.
When did minutes become SI units?
Oops.
Okay. Anyways, this is 3,600 seconds. Please do not repeat the same mistake. Okay.
Oh.
It's pretty childish. Okay. Now, time is equal to 3,600 seconds. Now, if you've gotten time, what's the total power work done during this time? Is it 20,000 joule? Is it 20,000? Yes or no?
Yeah. Yeah.
20,000 is just for one revolution. So in an entire time of 3,600 seconds, did the horse only turn the wheel once?
Yes.
Read the question again. It turned it 144 times. Do you see the term 144 times?
Yep.
So what's the total energy that it invested in turning it?
20,000 into 144.
Yes, and divide this by 3,600. Now listen up carefully. Over here, you are not going to use this 20,000 in your calculator, but instead you have a previous answer in your calculator, right?
Yeah. So I'm
You're
just going to
gonna,
press answer.
yes, you're gonna put in that value divided by 3,600 and give me the
Yeah,
answer.
I do that.
Okay, so what's the answer coming for it?
It cleared up. I'll have to do that again.
Okay, do it again, but you have to do it again. 2 pi
Okay.
into 3.7
2 into 3.7. Okay.
into pi. You have the pi
Okay.
in your calculator.
Yes. Yeah, yeah.
Okay,
I
and then
did that.
multiplied by 800.
Okay.
Now you must be getting 18,000 something.
Yes.
We multiply that by 144 and divide by 3,600 and you'll get your answer. Okay,
743.9.
743.9. Okay, now
Yes.
are you gonna leave it till here or you're gonna convert it to round it off to two significant figures as well?
Yeah.
So 740 is your final answer. It's the watts, 740 watts. Actually 740 watts, that's 1 horsepower approximately. Oh yeah, that's the power of a single horse. It's actually approximately 756 watts. Horsepower, do you know horsepower itself is a unit of power? Usually it is used in cars.
Yeah, I get that.
Yeah, so horsepower. This is what it actually means. It's the power generated by one horse. Okay?
Yeah, they specified that in the question.
Yes. They specified it in the question as well. So that's actually what makes physics very interesting, the real life situations which are in there. Okay,
I
and
still hate physics.
you still love physics?
Can we end the class now?